So this is um, a preparation for a talk scheduled today. The title is Deformation of Riemann surfaces and its natural generalizations into either higher dimension or other stuff. I want to be a part starting of a series on rigidity and deformations. Rigidity theory and moduli spaces. That's sort of the idea. So the motivation is this. Usually we want to work with irreducible polynomials. Like proving some polynomial is irreducible over Q, for example, is a difficult job, at least for me. There are multiple techniques, but a polynomial is irreducible if and only if its translate is irreducible. So if you translate it and then apply some criteria like Eisenstein criteria, then it becomes easy. Then it's possible to prove it in that way. So what should you do? Should you translate it? There is no actual algorithm. It's just a more of an art scheme, I guess. That is what I got from the course on Galois theory. Anyway, now I want to look at irreducible polynomials over C. Here are some examples. A good example is y square minus f, where f is like a product of linear factors. No powers, just distinct linear factors like z minus, so x minus zi, where all the zi's are distinct. That is a good example. Other good examples are written here. For example, x minus 1, whose real solution is this, whose real points are this. This is a rectangular hyperbola. We can see it has two connected components, the real points. But if I draw the picture in C2, it will be connected because it's irreducible, I think. Now what I want to do is, I want to follow along in this idea and look, see, polynomial is irreducible if and only if it's translated irreducible, its scaling is irreducible, and not just translate, if I translate, so do a linear transformation on the domain, the irreducible polynomials will still stay irreducible, I think. So ignoring the irreducible polynomials motivation now, what we want to look at is set of all polynomials of degree at most n. It's a vector space of some dimension, and let linear transformations act on it, translations act on it, and scaling by a non-zero polynomial act on it, non-zero scalar act on it, and then quotient by all these actions. So I want to look at a equivalence class of a polynomial up to translate a linear transformation of it, affine transformation of its domain, and scaling of the polynomial. So the dimension of this group is GL2 has dimension 4, complex dimension, and this has 2 and this has 1. So 4, 5, 6, 7. So if I subtract the dimension of the vector space minus 7, I sort of get a dimension of this space, the quotient space. This is not exactly correct. It might not even be a manifold. It might have connected components of different dimensions. It will not have connected components of different dimensions. It will not be housed off. So the 0 is like a fixed point. So that's a issue. I think it will not be a housed off space. So if I remove 0, then something, I could say something maybe. So this is why this dimension count is in a bug box. This is not exactly correct. If I take so this is a smooth Lie group action, I guess. Yeah. If I take an orbit, then orbit quotient of stabilizer, or the dimension of the group minus, there will be a stabilizer as well. That is why the dimension count might be smaller than this. Yeah, but let's call this a generic dimension or something like that, and this is that dimension. So if there is no if an orbit has no stabilizer, then um, this. Oh no, I'm talking about something else. Never mind. So this question space might not be a manifold. Uh, I'm not. I was thinking about the dimension of the orbit. I'm talking. I should be talking about the dimension of the quotient space. So there might be a weird thing going on here. It will be connected because it's an image of a connected set, continuous image of a connected set. But if I remove zero, it might not be connected anymore. Oh, if I remove zero, it will still be connected, but things might happen. Okay. Now consider homogeneous polynomials. So if I take a polynomial of degree at most n, I can homogenize to homogeneous polynomial of three variables, one variable higher, of degree of homogeneous degree n, and this is a bijection. These vector spaces have Simon dimension, for example, in particular. I mean, now one thing we can notice is if I act on these homogeneous polynomials by project GL3 maps, these will scale the polynomial, because I'm also considering scaling GL3 also as scaling linear maps, and it will also translate in the XY variables, and it will also have linear transformation in the XY variable. This is easy to check. So this quotient space going to this quotient space makes sense, but the generic dimension of the domain is 2 dimension higher. So a generic fiber, this is all bug boxes. There is no way to properly write this in terms of manifolds. But if I take a polynomial here and then look at its pre-image, it will generically be of dimension 2. That's the sort of the heuristic idea of the dimension count. So I want to look at two variable polynomials up to these translations, but I can look at the whole fiber of the image together. They are sort of the same polynomial in some sense. So this is, you can make this more precise by saying all these fibers are affine part of a same of the same projective curve. Yeah. I mean, the polynomials might be reducible, but okay. Affine part of a algebraic affine projective set. Now, projective algebraic set. Now, this is motivation for what I want to do. So this motivation is saying that we can do dimension counts of polynomials. Okay? Will be uncountably many polynomials, even up to projective. Even if I homogenize them and then quotient by a dimension 9 group, I will still get a higher dimensional. So this space has a dimension. So there are uncountably many irreducible polynomials. So irreducible polynomials will be an open set in here, because reducibility will demand a closed set. I think so. I'm not sure, but yeah. So this is the dimension of moduli space of plane curves. Yeah, because it's supposed to be an open set in this quotient, and yeah, this is the dimension count. So classifying complex polynomials, irreducible complex polynomials, is equal to classifying plane curves up to projected linear transformations up to isomorphism, and some of them will be smooth. Smooth ones will be open here, because smooth means it's zero, so some derivatives is zero, so it will be closed. No, smooth means something is non-zero, so it will be a complement of a closed set, I think. So, so this represents all projective algebraic sets up to isomorphism. We can take the reducible ones, and we can take even the smooth ones inside them, smooth reducible ones. Now, to study that, study all curves like that, we can rather study the Riemann surfaces. So, if I take a zero set of a polynomial in two variables, I will generically get a Riemann surface. So if the polynomial satisfies certain conditions, this derivative does not vanish along with the polynomial. So the pre-image is a smooth manifold. It will also have a structure of a complex manifold, complex one manifold. So real dimension 2. Which means so it's a smooth manifold with transition functions from Cn to Cn, where n equals to 1 in our case. They will be holomorphic. And this is a complex one manifold, and Riemann surfaces will be are defined to be connected complex one manifolds. Now, zero set of polynomials might be not connected, of course, but I think irreducibility will be even only as connectedness of these zero sets. So rather than classifying polynomials, we can classify these Riemann surfaces for a given property or given smooth structure. So given a smooth manifold of dimension 2, how many Riemann surfaces structures does it contain? That's sort of what I want to do in the first half of the talk. And then we wish to generalize that idea into higher dimensions or different cases. So easy examples of Riemann surfaces are open subsets of C. So C is open subset of C, and O unit disk is open subset of C. So we can ask if these are biholomorphic. So biholomorphism of complex manifolds is a homeomorphism, which is holomorphic map is a continuous map, which says that if I bring it onto charts, so this going to another manifold like that, if I bring it onto charts, then that map from C to C, so I'm talking about Riemann surfaces, map will be from C1 to C1, that will be holomorphic. So if that happens, then we call the map between continuous map between the Riemann surfaces to be holomorphic. And we want to classify Riemann surfaces up to biholomorphism. That is exactly related to classifying polynomials like this or algebraic curves like this up to projective linear transformations. Yeah. So let's start. So it's an easy fact to prove using basic complex analysis that C. So there is no biholomorphism from C and D between C and D. Unit disk and the entire complex plane, complex line, whatever. And it is also an easy exercise to show that there is a biholomorphism from the upper half plane to the unit disk. So upper half plane looks like there is a biholomorphism between them. Now, and we can show that these are so C and D and upper half plane are all homeomorphic, but we can see there are two complex structures on this homeomorphism class. So there are the complex structure of C and the complex structure of upper half plane, and we can show, and this is the non-trivial theorem called uniformization of non-compact Riemann surfaces. These are the only ones, and these two are the only simply generated non-compact Riemann surfaces. But ignoring that, let's go to complex cylinders. Cylinder is a smooth manifold defined to be x1 cross r. So this is r direction, this is the circle direction, and we can show its topology. So it's homeomorphic to, it's not even homeomorphic, it's diffeomorphic to the open subset of R2, which is R2 minus a point, minus 0. So given this diffeomorphism type, diffeomorphism class, how many small Riemann surface structures does it have? It actually has many. It doesn't have two, it has even more. I'm exactly not sure about the exact classification, but let's do this. So C minus 0 So how do we understand these ones? We can understand them by looking at their universal covers. So consider the map which is exponential, complex exponential. This map is very nice. It satisfies the property which is called being a covering map. It's surjective in particular, and a local homeomorphism, but it's even stronger than that. It satisfies something about the pre-image, and we can restrict this. Shows that C minus 0 is isomorphic to C quotient Zi. And this implies d going to exponential of d minus 0. So d minus 0 is isomorphic to d quotient. Z in some sense. This is, but there are even more. We can construct even more kinds of surfaces, so cylinders, complex cylinders, which is consider upper half plane and consider a point real number L. Then Z goes to Z plus L. This map. So consider the upper half plane quotient this I. This will also be a cylinder. These two ends will be identified. let's move everything. Yeah, so that these are also there, and these are all non-isomorphic, I think. Because these are there. Now we can move on to some other examples, like take a torus, and how many smooth structures, how many Riemann surface structures does it have? It actually has a lot, like uncountably many, and they are all of the form C quotient